All right, in this video we're going to talk about integration in spherical coordinates. And what we're looking at here is a differential volume element in spherical coordinates. And just like what we did for cylindrical coordinates, we first want to figure out how to find the volume of one of these little curved boxes. And then we'll look at how to set up a triple integral in spherical coordinates. So to start, let's go ahead and consider this radial distance you see in green from the origin out to this corner of the box, and we'll label that distance rho. And now if I increase rho a little bit, I'm going to just move radially outward along this edge here. So the small change in rho you see in orange is what we'll label as d rho. Okay, so now let's consider this angle phi, which is formed by the positive z-axis and this radial segment from the origin out to this corner. Okay, and now imagine increasing phi a little bit. Okay, so as we rotate forward d phi amount, just a little small change in phi, okay, we're going to now trace out this circular arc here, which is going to form this edge of our box. And to measure the length of this yellow circular arc, well, the radius of the circle is rho, that's just the green segment, and the central angle is d phi, so this yellow circular arc will have length rho times d phi. All right, and then for the most complicated part, let's consider the distance from the z-axis out to this corner right here. Okay, now that is just the polar distance r. And in the previous video, we had argued that r was equal to rho times sine phi. And we did that by just looking at this right triangle here, formed from the origin out to this corner of our box, and then out to this point on the z-axis. Now this angle here is phi, and this hypotenuse is rho. So if I take the sine of phi, I'm going to get this opposite side length, which is the red length you see here, and then I'm going to divide that by the hypotenuse, which is rho. And so put another way, r is just rho sine phi. So that's this distance right here. Now, if I rotate this red length through a small differential angle d theta, I'm going to carve out this little circular arc in purple. And to measure its length, I'm going to take the radius here, which is just the red length, so rho sine phi, and then multiply that by the central angle, which is d theta. So this product right here, rho sine phi d theta, gives me the length of this little purple circular arc. Okay, so now with all of that, we can go ahead and compute the volume of this little curved box as the height, d rho, times this little yellow circular arc, which is rho d phi, times then this purple circular arc, which is rho sine phi d theta. And we can rewrite that as just rho squared sine phi d rho d phi d theta. Okay, so now with this in place, our triple integral can be set up as follows. Okay, we're going to replace x with that expression we derived in the last video. So x in spherical coordinates is rho sine phi cos theta. Then replace y with its spherical representation. That was rho sine phi sine theta. And then lastly, z was rho cos phi. And then here we have our differential volume element dv in spherical, which is quite a bit more complicated than what we saw for cylindrical coordinates. And although this thing does look like a horrendous mess, if you integrate over regions bounded by nice surfaces in spherical coordinates, so namely things like spheres, this oftentimes is a fairly simple integral to compute. So we'll go ahead and illustrate that very thing in the next video. All right, thanks.